Space nuclear power enables us to generate continuous heat and electricity in places like the shadow craters of the Moon or in the deep solar system, where we just don't have access to continuous power.
We're really solving two challenges of reutilizing what would have been classed as a waste product, at the same time addressing the challenge of how you generate power in space.
So we've been trying to hone in on a recipe that not only produces us a stable, high-density pellet, but it's also highly scalable, and that's the key to really being able to deliver nuclear power systems for space.
And what actually is the recipe, can you tell me?
So that's proprietary knowledge, so I can't disclose that here.
If you look at most spacecraft, you tend to see these things. Big, shiny solar panels. They're an obvious solution for generating power, but they have limitations. They're cumbersome, they don't work in shadow, and they're less effective the further you get from the sun. As we send spacecraft deeper into the solar system, could nuclear fuel be a promising alternative? In the UK, a spin-out from the University of Leicester called Perpetual Atomics has been developing technology that uses byproducts from nuclear reactors on Earth to power missions in space.
Nuclear is extremely appealing because it's the most energy-dense fuel form that we could use in a space environment. So the fuel that we use is americium-241. It's actually a byproduct of reprocessed civil nuclear fuel. So when you reprocess nuclear fuel, you get plutonium and you get uranium. That plutonium, that uranium can be reused. But if you're storing the plutonium for extended periods of time, the plutonium-241 decays into americium-241. It really becomes a contaminant if you're trying to reuse that plutonium.
The decay of americium-241 produces a steady stream of heat, which can be harnessed for space missions inside devices like these. But turning a nuclear waste product into a usable fuel has been a major challenge.
Americium-241 likes to undergo different crystal structure changes. And because of that, it typically cracks when you try and make a solid structure, such as the pellet in my hand. So one of the things we've been working on is adding an ingredient in a recipe that allows it to be stable during that process. We've had to come up with a way to be able to trial different recipes, trial different processes and procedures without actually having to work on a radioactive material. And so one of the ways we do that is we use surrogates. So surrogates are materials that, in a solid state chemistry perspective, behave very similar to americium, but is non-radioactive. And so actually the glove box behind me is the facility that we use to do that. We've managed to create, for the first time, a stable fuel form that's highly scalable. And we've now transferred that into the nuclear environment with partners in the US. So they're able to take the recipe that we devised to actually produce the first ever solid americium-241 pellets for spaceflight.
Space launches have the potential to go spectacularly wrong, so any nuclear power system on board has to be designed to withstand worst-case scenarios.
So in case of an unexpected accident, like a launcher explosion during the takeoff, we want to minimize the release of nuclear material into the environment. To do this, the current approach for heat sources is an approach called containment and confinement. We want to contain the fuel as much as possible. In our system, there are multiple layers. They all protect the fuel from an accidental release.
So this is a welded platinum-rhodium clad, which allows us to encapsulate our fuel in a metallic structure that can survive projectile impact, shrapnel impact from worst-case accident scenarios like the launch vehicle exploding or the spacecraft coming back to Earth and impacting against the ground. So under extreme impact scenarios, the platinum-rhodium alloy can deform and behave very plastic, a little bit like Play-Doh being struck against the wall. The next form is to get it in a structure which can survive some of the other accident scenarios. So this is a carbon-carbon composite structure, and so this is effectively our thermal protection system. In a scenario where the system needs to re-enter the Earth's atmosphere, it needs to survive the high and aggressive heating loads, carbon-carbon based materials allow us to ablate away that heat Once you've got to this stage, this is what we call the RHU, the radioisotope heater unit.
One of the first missions that this heater unit will be utilised for is on board the Rosalind Franklin rover, which the European Space Agency plans to send to the surface of Mars by the end of the decade.
The radioisotope heater unit that we've been developing will actually be used on the landing platform, and by having the RHU on board, it keeps everything warm and therefore it lets the battery last that little bit longer so that the rover can go through its pre-deployment checks before it begins its mission on the surface. But it's not just in space where these type of systems can be used. Nuclear power systems can be utilised here on Earth, for example, in the deep ocean, where we want continuous power without needing long cables connected to some sort of external power supply.
So this particular one sitting here is an example of the mechanical holding structure that will be used for the Rosalind Franklin mission on the landing platform. And so as you can imagine, that RHU structure would live inside this gold metallic structure, fixed to the spacecraft, able to survive the vibrations, the shocks, and the thermal cycling environment that the spacecraft is going to go through.
Nuclear power could also help us to explore the surface of our nearest celestial neighbour.
There's been a big push to using this type of power solution on the moon to address the biggest challenge, which is lunar night survival. On the moon, we have generally around 14 days of daylight, followed by 14 days of darkness. And these are the only types of systems that can allow us to operate through the lunar night and then survive onwards through multiple lunar cycles. And that is going to be critical to us having a continued operation on the lunar surface and ultimately build our lunar base.
As well as producing heat, the radioactive material can also be used to generate electricity.
So this is a thermoelectric module. This uses semiconductors to convert roughly 5% of that heat into usable energy. And so we take the same building blocks of the heat source, like we saw with the radioisotope heater unit, but into a much larger structure. So instead of 3 watts thermal, we're now generating roughly 200 watts thermal. And then we can integrate that into a power generating system. So that's taking the heat produced from the heat source, converting some of it using thermoelectrics, and then radiating the rest, either to be used to keep the spacecraft warm or just dumping it into the environment.
Building on this work, the team has also been developing a more efficient kind of power generator, which uses an engine to turn heat into motion and then into electricity.
This type of system just has not been flown before. It has moving parts and it adds that extra level of complexity. But what we've shown with our systems is that we can lose an engine and still generate just as much electricity, which makes this power system really robust and really reap the rewards of having a power source such as americium, which generates heat for decades.
Nuclear power has the potential to unlock new kinds of space mission and new kinds of science, but the researchers behind this technology are thinking even further ahead.
So the work that we're doing on radioisotope power systems is really enabling our ambition to do many more things in the space domain. How are we going to explore Mars? How are we going to explore the outer solar system? How are we going to do that routinely and without worrying about availability of power in those environments? Our ultimate goal really is to become a utility company in space, both in terms of space science, in terms of exploration, and in terms of building out that infrastructure in space.